Welcome back, Physical Science 20. This is the beginning of the FC2 unit, the unit on the mole, and understanding the mole and looking at it as the amount of substance for measuring. So, first one here, a mole, a unit of counting. So we'll discuss how to measure quantities of substances that are not readily countable, such as a huge amount of things. Relate counting by weighing in real-life applications. Provide examples to demonstrate exactly how big this number is to common items. And explain why chemists use that number to represent the amount of substance. And that will filter into FC2.1 as well. So the mole, a unit of counting. How is a balanced chemical equation like a recipe? Balanced chemical equation not only tells you the ingredients, so if we take a look here, the ingredients, but also the proportions in which they react. So 1 to 1 to 2 from the coefficients. So consider, for example, the equation for the synthesis of hydrogen chloride from its elements. The equation tells us that 1 molecule of hydrogen and 1 molecule of chlorine produces 2 molecules of hydrogen chloride. Hydrogen atoms and chloride molecules are incredibly small, too small to be seen even with a powerful microscope. The reaction in the figure below, for example, represents an astronomically large number of reacting molecules. So if we have it this way. And yet chemists can combine them in the right quantities of hydrogen and chlorine so that when they both react, both substances will be completely used up, as in this case. How do you count entities as small as atoms and molecules? Counting them directly as you would count students in a classroom is not technically possible. And even if it were, there are more molecules in this flask down here than you could count in a lifetime. Therefore, chemists need a more convenient way to determine how many particles, such as atoms or molecules, are in a sample of matter. So if you look at the next page, using mass to estimate numbers. So earlier you would have done the counting estimates lab, in which you determined the number of beans or the number of grains of rice in 1 kilogram or 1,000 grams, using the total mass of the sample. All you needed to know was the average mass of a bean. However, whatever method you used for that. And then you could figure out how much are in a larger amount. So in the figure above shows masses of tennis balls and golf balls. The total mass of the tennis balls is 672.7 Gs. If we had been told that the mass of one ball is 56, so if we knew on average that the mass of one tennis ball is 56, then we could figure out the total here. So if we have 672.7 grams total, and if we know the conversion here, that one tennis ball represents 56 grams, then we could arrive at the conclusion that there is 12. And of course, with this small amount, we could actually count it. Similarly, if you did the same thing with golf balls, so if we had 540 grams as a total, and if we knew on average those golf balls were 45.2, so 45.2 is one golf ball, we could get 11.9 golf balls. And of course, we wouldn't say 11.9, we would round it up to the next whole number. This uncertainty is due to a number of factors, such as limitations of the measuring device, slight variations from one ball to the next. In conclusion, the use of measurements such as mass can only give an estimate of the number of entities in a given collection. It can never give an exact value. The only way to know for sure is to physically count them. In the case of a few identical balls on a balance, the estimate is very good. The estimate may not be as good for larger numbers of objects, such as grains of rice in a 1 kilogram bag. So we may be off by quite a bit where that's concerned. The use of measurements such as mass, so using mass to count things, has some important applications. For example, industries commonly use mass to indirectly determine the number of small parts, such as nuts and bolts, in their inventory. So if you bought a bag of nails at a hardware store, at the cashier, they would likely know the average mass of one nail, so they can mass the whole bag. They could determine how many nails are in that bag. Also, automatic coin counting machines, such as in this picture here. Use measurement to sort and count money, as in the figure above. In some counting machines, coins are first sorted into stacks according to type. Then the height or mass of each stack is used to determine the number of coins present. These measurements are used to calculate the total value of the money inserted into the machine. So there we go. Those are some examples of using mass to count things. So with that, we move on to the mole, which is referred to sometimes as a chemist's dozen. So if we look over here, 1 dozen equals 12 things, as we know. The word six-pack means 6. A ream. If you had a ream of paper, that's actually 500 sheets. 1 hour is 60 minutes. And so we can add this here. 1 mole is equivalent to 6.02 times 10 to the 23rd things, whatever that is we're talking about. So a dozen is a common counting unit. A counting unit is a convenient number that makes it easier to count objects. We often count donuts and eggs by the dozen. We count shoes and gloves by pairs. So the table on the right gives some other ideas. Chemists, however, do not work with the macroscopic or visible objects like shoes and donuts. Instead, chemists are interested in microscopic entities, atoms and molecules. Since these are so small, we need to have a huge amount of them in order to measure them, and that's where the mole comes in. So what is the mole? So first of all, the shortened version of it is just MOL, so dropping off the E, which is kind of funny. It's the SI, or System International, base unit for amount of substance. 1 mole is equivalent to this big number here, or we usually like to do it in scientific notation, 6.02 times 10 to the 23. These particles could be anything from electrons to atoms to stars. However, for practical purposes in chemistry, the mole is used to count microscopic things such as atoms, molecules, and formula units. Sometimes ions as well, as we'll see. The value of 6.02 times 10 to the 23rd is sometimes called Avogadro's number, named after good old Amadeo Avogadro himself. So yes, Amadeo Avogadro. Avogadro's constant is determined experimentally, and in the next section we'll take a look at how that was achieved. As experimental methods improve, the value of the constant becomes more precise, so currently it's 6.02214199 times 10 to the 23, but for our purposes we could just simply round it off to 6.02 times 10 to the 23rd. So you may wonder why chemists did not choose a more convenient number, for example a trillion, but there is logic behind it. Like other SI units, such as the meter and kilogram, the mole is defined against a known standard. The standard chosen is to be exactly 12 grams of carbon, and in particular the carbon-12 isotopes, which has 6 protons, 6 neutrons, and 6 electrons circulating around it. Scientists have experimentally determined that exactly 12 grams of carbon-12 contains that number. And we'll look at that in the next section. So remember that a mole is a counting unit just like a dozen. So whenever you see the word mole, just think of it synonymously as dozen, in that it's a word that describes a certain number of things. However, instead of counting atoms by the dozen, chemists count by the mole. So for example, the figure below right shows equal numbers of carbon atoms and sulfur atoms. So in other words, we have a mole of each. We have 6.02 times 10 to the 23rd carbons and 6.02 times 10 to the 23rd sulfur atoms. Sulfur, now if you take a look here, if you were to put that on a balance, carbon is, well, 1 mole, yes, is 12.01. Sulfur is 32.06. And you can see here that the sulfur atom is bigger than a carbon atom. So the sulfur sample has a larger volume and a greater mass because the atoms are larger. It'd be like comparing basketballs to ping pong balls. Similarly, a dozen tennis balls occupy a larger volume than a dozen golf balls. So note that just as volume of a substance is measured in liters, the amount of substance is measured in moles. Scientists use moles to communicate the amount of tiny particles such as subatomic particles, atoms, formula units, and molecules, just as a package of donuts contains 12 donuts. So how big is a mole? It's difficult to comprehend just exactly how big it is, but I do have an analogy on the next page which will hopefully help. So I like to refer to it as the green pea analogy. So if you were to imagine a teacup, we can fit about 100 peas in there, 100 frozen peas, which seems more than it should be. But if we looked at the volume of a teacup, the volume of an individual pea, there can be 100. Refrigerator, we can fit 1,000,000 peas. Again, if we can figure out the length times width times height of this cubic structure, i.e. a refrigerator, and if we know the volume of a single pea, we can figure it out. An average 3-bedroom home, 1 billion. All the homes in a small town, 1 trillion. All the homes in a large city such as Hamilton, 10 to the 15. 1/2 of Ontario covered 1 meter deep in peas, 10 to the 18. And recall that the mole is 6.02 times 10 to the 23. 23. And here we're only up to 10 to the 18. All the continents covered 1 meter deep in peas, 10 to the 21. And if I was looking at 250 planets like the size of the Earth, all of them covered 1 meter deep in peas. Now we're getting closer, but still we're only 1/6 the size of a mole. So the values in the table above are determined using the following reason. 100 peas fit into a teacup of known volume. If the volume of a refrigerator is known, then yes, the number of green peas that would fit in there could be calculated by division. All right, so you should be able to do the assignment now for that, and that serves as the introduction. So that was FC 2.1. We'll see you again.